Hello and welcome to Groundhog Graphics Retro. My name is Martin, and this video we are going to discuss how to auto-detect the size of a RAM expansion unit. In our last video we talked about how to auto-detect if a RAM expansion unit was actually plugged into the machine. Now we're going to go ahead and talk about how to detect what size RAM expansion unit is installed.
Let's take a look at a Commodore 1750 512K RAM expansion unit. On the left we have banks 0 through 7 for a total of 8 banks. And in the middle here is memory, which is always 64K of RAM per bank. Since there is no direct way to ask the RAM expansion unit how much RAM it has, we have to exploit a limitation of the RAM expansion unit to find out how much RAM is in it. Let me show you. Let's take a look at REU bank. Notice that bits 3 through 7 are all ones. On the 512K model, that means that these bits are completely not used. Only bits 0, 1, and 2 will affect which bank is being pointed to. Because of this limitation, we will use this to our advantage to determine how many banks exist in the RAM expansion unit. So now notice we have the bank numbers and we have their binary counterparts to the right. So any bank number that we enter now over the number 7 will act as a shadow bank. Let me show you. Let's enter 8 as a bank number. Notice the first 3 bits did not change. Let's go ahead and enter 9. And the first 3 bits again didn't change. Let's see the rest. So what this means is that bank 8 is the equivalent to bank 0, and bank 15 is the equivalent to bank 7. And once we go and we poke in, let's say 16 will then be the equivalent to bank 0, and the process will continue to repeat. So now that we understand this portion, let's go and run a program that I've made that will demonstrate the entire technique. This program is a simulation. It does not actually access the RAM expansion unit, but it simulates the process we use to determine the size of the REU. So this allows us to select the number of banks so we can simulate different size RAM expansion units. Right now, I'm going to go with the 512K 8-bank RAM expansion unit. As we can see on the left, it says bank 0 through 7. Those are 8 banks, and those simulate the actual real banks of the RAM expansion unit. To the right, it says shadow. Now that will be the bank number that we will be poking into a RAM expansion unit that we don't know what size it is. So we will actually poke all the way from 0 to 255 because we don't know what size the RAM expansion unit is. So next, counter. We begin the counter at 255 and we count backwards and we count all the way down to 0. So what we're doing is the opposite. We're starting at bank 0, counting up to 255. The counter, we are counting from 255 back down to 0. While we count backwards, we are storing each counter number in the first byte of the RAM expansion unit in each bank. And to the right of that is the shadow binary. That is simply a binary representation of what we are poking in the shadow register. In this example, you will see that only the first 3 bits remain this. Well, they change, but then they remain the same after we go from bank 8 and forward. So let's go ahead and begin. I have to hit the key every time that to show each number as it goes through. So when we get towards the end, I'll slow down. Now when we go to bank 8, notice it repeats. but still the right three digits are zeros. 9, notice no change on the right three digits. Now I'm going to go faster. And what we're doing is we're going down until the counter reaches 0 and the shadow register reaches 255. Then you can see to the right, the first three bits remain the same. And here we are, one step before it finishes. So now I'm going to continue on, and you see counter is at 7, 6, and that's it. Now our program would have completed. If you notice that in bank 0, the first memory location would have a 7 in it because this has 8 banks. The shadow registers would have overwritten bank 0 several times, and now that we've gotten to the very last numbers of our counter, we've gone to 0. The remaining number of banks is left in bank 0. Now it is not the total banks, but it is representative of the actual bank number. To get the total banks, you simply add 1. So let's do the process again. This time, let's try a 128K RAM expansion unit. And that would be 2 banks. Now you see we only have bank 0 and 1. Now with the 128K RAM expansion unit, it will only use the very first binary digit, digit 0. And every other digit beyond that will be ignored. So I'm going to begin counting down. And now here we are getting close to the end. I'm going to slow it down. And there's counters at 2, counters at 1, counters at 0, end of process. And we notice that shadow register 254 is equal to bank 0, and in bank 0 we have stored 1. So it is representative, like I said, of the actual last bank number in the RAM expansion unit. Add 1 to it and you have 2 banks. Let's go ahead and do one more real quick. We'll do a let's do a 1 megabyte, which would be 16 banks. And I'll go ahead and run through. Okay, now we are getting close to the final run. We are down to the counter is down to 16. There's 15, 14, 13, 12, all the way down to 0. That would be the end of our function. We can see that the shadow register that we poked 240 into the bank, but that was equal to bank 0 in the REU, and we placed a 15 in the first memory location 0, and it has left a 15, which the last bank of a 1 megabyte RAM expansion unit would be 15. Add 1, 16 banks. So now it's time to get into the code. This is C code, but even if you're not familiar with C, I will try to simplify it as much as possible. At the very beginning, I have a structure called REU regs, which stands for REU registers. And if you are familiar with modern programming languages, this is a class, pretty much exactly like a class. And it is the blueprint for all the registers that are in the RAM expansion unit. Now, by creating this structure, I can create a pointer of this type, and I can also assign that pointer directly to DF00, which is the very beginning of the RAM expansion unit registers. Therefore, I don't have to refer to each register by their address. I can refer to them by name and and obviously a data type. Now let's scroll down to the function that actually determines the size of the RAM expansion unit. Okay, so at the very top we have integer a, and I'm just using that as a whatever variable. Just I'm using it to our counter down here below. Below the integer we have the character buffer and bank. The buffer is where we're going to store all of the data that's currently in the RAM expansion unit. Because when we go through each and every bank, we're going to write to the first memory location of each and every bank, and we want to save that data just in case there is some sort of valuable data in there. We don't want to corrupt it. Next, I have REU regs. Remember, that is all of the registers listed in order that they would appear in memory, so we can refer to them by name. Now, I've created one of them to be an overlay, which is REU base. I assign that to memory location DF00 because it's REU right here is a pointer, and REU base is our DF00. Sorry about that. So REU pointer gets assigned to REU base address DF00, and then old REU is an actual variable, and that will be used to store all of the current settings that are in the RAM expansion unit registers. It will save those because we can restore them later. So that way everything, when we're done with this routine, will seem like it's pretty much untouched, with the exception, of course, of a status flag or something like that. For like DF00 status register, that would get cleared, and there's nothing we can really do to do anything. We can't do anything about that because once you read it, that bit gets cleared and you can't write to it. But we do the best we can. So now, down below, I have buff, which is our buffer. I allocate it right here, so we have somewhere to store all of the RAM expansion unit data. And down below, I have bcopy, and this will copy all of the registers that control the RAM expansion unit, and it will copy them from REU, which is DF00, and it will copy it to the address of the variable old REU, wherever that address is, and of course its size of the REU registers. Next, we are going to set up our RAM expansion unit registers for transferring, and we're going to set up Commodore address CAD to equal our buffer for storing the data that's in the RAM expansion unit to preserve it. Then we will go and set RAM address RADD RAM expansion unit address to 0. We will fix the RAM expansion address to 0 by changing address control bit 6 to a 1. And then we will set our transfer length to 1, and then we'll go down to our for loop. So this is our loop that does the heavy lifting to find out the size of the RAM expansion unit. The loop counts from 0 to 255. We see that we have buff plus a, a pointer to our buffer, and that will equal 255 minus a. So what that does is it reverses the counter in our for loop. So if our for loop is equal to 0, 255 minus 0, that means that buff plus a will equal 255. So then, next, REU RBank selects the actual RAM expansion unit bank, which selects all the banks from 0 to 255, all the possible banks. And then we have REU RCOM, which is our command to transfer, and not transfer, but actually swap. And what it does is it performs a swap between the buff plus A and the RAM expansion unit. So what it does is it places the counter that we just stored in buff plus A. It takes that, puts it in the RAM expansion unit. Whatever was in that RAM expansion unit slot, it places it back into our buffer, so we can restore those contents later. Okay, so now right after our loop is completed and we put all of the counter numbers into the RAM expansion unit, we are going to change the C address to a variable called bank to store what bank number is in bank 0, memory location 0 of the RAM expansion unit, because we know this number will be the number of the representative of the very last bank that is actually in our RAM expansion unit. So C address equals that variable address, our bank equals 0, and then our command is a transfer from the RAM expansion unit to um, to the C address, which is pointed to bank, and that will be that value telling us what is the last bank in this RAM expansion unit. Now we have that stored. We go down, we restore the REU data, so we point C address to buffer, which has the first, it has the first byte that was in each bank stored in it. So now we just go through each bank and put that memory right back in, so we don't corrupt anything if there's any valuable data in it. So here's our loop to do that, and all we have to do is take our for loop and go through the number of banks and just put that data back in. Now I'm going to warn you guys that this particular function for restoring the data that was in the RAM expansion unit, I have not tested yet. I think it works, but thinking it works and if it actually works can be two very different things. So, if you do run this code, make sure that you're a little wary of that particular part, because I just haven't had a chance to test it yet. Finally, we do a little cleanup. The free deletes our buffer. We don't need it anymore. And we restore the registers the way they were for the most part before we started this routine. Now, something I could suggest if you guys want to use this routine, I myself may even get rid of it, is the restoring these RAM expansion control registers. This is not absolutely necessary. I mean, it's not going to corrupt data. I mean, obviously, if you pay attention to what you're doing with your registers, this really could be removed and make it a little bit smaller code. It might make it slightly faster, but that's not going to be significant. It's mostly just reduce the size. And then, of course, at the end, we will add one more number to the bank, so we get the actual total number of banks. I did see a way to improve the code a little bit. Up here at our for loop, I have a less than bank plus 1. Now, I've already made bank a character, so its maximum value is 255, and I've already recorded showing you guys, that particular set of variables. So instead of having to delete all that and re-record, I'm just going to go ahead, it's a minor thing, and just proceed with this video. However, I'm probably going to take bank, change it from a character variable to an integer so it can actually hold 256, and then after we do our bank transfer, then probably immediately right after our I'll put a increment to increment the bank, and then when we come down here to our for loop, we don't have to add 1 each and every iteration of the loop. Once again, it's just a minor improvement, and I'm not going to go ahead and re-record just for that little fix. I'm sure there's always kinds of little improvements. I'm sure there's be more improvements after this even. And that's where hopefully you guys come in, and maybe you guys can make some improvements to it and let me see what you got. That'd be really neat. Alright, so let's go ahead and head up. Okay, so we scroll up to our main function, then we come back down, and we go to our printf functions in this while loop. So basically this is pretty simple. If you look at the if statement, we first check to see if there is a RAM expansion unit actually plugged into the Commodore with rdetect. If that returns a true, which is a non-zero number, then we will go ahead and create an integer for banks, and we will take banks and we will store our size, which we just went through the function, and it returns a number of banks plus 1, which could be as much as 256 banks, so it has to be an integer. And then below that we printf the REU, the number of banks that we have, and then to print the amount of RAM that we have, we simply multiply the banks by 64, and we add a little k to it, so we have 64,000 bytes. If we have however many banks we multiply, we can have 128k or 512k or whatever on the screen. Obviously, if I tried to store like 512k without the k, just fully in a variable, C doesn't support that. It only supports up to 65,535 as the largest integer size for 2 bytes that it supports. So I just went ahead and did the K, easier for us to read, and works in C. So I guess what we're going to do now is go ahead and see how this program runs, see how it works. Okay, so now I'm going to go ahead and run this program, REU %. And when I run this, it will automatically detect if there's a RAM expansion unit installed, and it will also give us the size. I'm currently running this in the Vice emulator. So what it does is it continues to loop and tell you if you have a RAM expansion unit installed, what size it is, until you press E to end. So I'm going to go ahead and press enter. Right now we have a RAM expansion unit detected, banks 8, 512K. Let's go ahead and change that. Alt-O. And let's try a 128K. See if it works. Oh, it was set for 256K. I'll get to that in a moment. I'll tell you exactly why that problem is only in the emulator. 128K, and there we have it, 2 banks, 128K. And if we go for a 16 megabyte, and you can see it detects 256 banks and 16,384K. So that's 16 megabytes. Now, why it was set at 256K and told us it was a 512K? Well, that's because Vice is actually only emulating 3 different RAM expansion units. It emulates a 128K, a 512K, and a 16 megabyte. All of these others, like 1 megabyte up to 8 megabyte, are all actually 16 megabyte. The 256K unit is actually just a 512K unit, and the 128K is the only one that is unique in Vice. I have tested all of these routines, not with real RAM expansion units, only one real RAM expansion unit, but I have tested them with the 1541 Ultimate cartridge, and I've tested it with multiple RAM expansion units, and all of those come out exactly right. So it just depends on your emulation and how much work they put into the emulation. And this one, like I said, there's only 3. So if you try this program out and you have a different RAM expansion unit or a real one that you can test it on, by all means, give it a shot. But I've tested it on everything that I can test it on. Now, as far as my real hardware, I would love to show you that, but I don't have any way to really capture the video properly, so I'm kind of stuck with the emulator. So now, I do have some functions I've made, little add-ons for the REU that we can go over, and you guys can then, of course, download them and use them in PowerC if you'd like to. Okay, so now we can go over some of the functions and additions that I've added, and that way you guys can see how to use them, or if you want to use them. Let's see. So we have R detect. I try to keep R's in front of all the RAM expansion unit functions. So R detect will return a 0 if there is no RAM expansion unit attached to the computer, and it will return a 1 if there is. R size does not return the RAM, it returns the number of banks, the total number of banks that are currently attached to the system. Next, I have my structure, REU registers, and this is handy. You can use this like an overlay. You see I have character for each particular memory location, and I have the data type for each memory location. So like C address, obviously, that would be a 2-byte unsigned value, and that's what it is. And so you can use these like an overlay, and I'll show you right now. You see down here, right below type def, we have REU regs, and I've created a pointer. Called it REU, you can call it anything you like, and it equals df00. Now that's the base address of where you see up above rstat, the character rstat will equal df00. And let's see here. Also, if you're used to using your structures and you go, oh, well, maybe this doesn't line up because the structures have those packing differences between characters and integers and all that stuff, don't worry about it. In the Commodore, none of these structures do that. They're all just one byte after another, so there is no sort of spacing in their padding. That's what it is. There's no padding in there, so you don't have to worry about it. So now you create the REU register or variable, a pointer type, df00, and then you come down and you say REU C address equals 1024, which would be screen memory, and R address would be the RAM expansion unit address, and let's just say 0, and RAM expansion bank is 0, and transfer, notice the L on the end, I kept forgetting that myself, but that stands for transfer length equals 1000. And then you have REU RCOM, which is the command register, and that's where you would execute and finalize um, your transfer from. So now I've also got a little bit more. And if you don't want to do all your transfers manually, like you have to up here, I've created a function that will do all the different transfers, stash, fetch, and swap. Now the function is not listed. The function is simply named REU. But what I decided to do was to create some macros. And if you notice, my macros rstash, rfetch, rswap, those are camel case. And it's okay for a macro, but don't ever do that for your functions in C. You will have problems later on when you try to add functions to the library, and the library won't notice them. And additionally, don't use an underscore for the very first character if you plan to use it in a library somewhere, just so you know. So we have rstash, rfetch, rswap, and I see rstash, I have C64 memory, REU bank, transfer length, and then the ones below I just filled in the positions, and each one takes the same parameters, the same number of parameters, and so it's all basically the same thing. So you can stash, you can fetch, and you can swap from the RAM expansion unit. So that's pretty cool. And let's see. Also, yes, there is a file that will have information in it. It'll be reu.doc, D-O-C, and that will have information on all of these commands and things too inside of it. And there is a D64 file that has all these functions on it and the macros, and these macros are located in reu.h header file, and so that's where the macros are, and that's where the structure is as well. So okay, let's continue. Okay, some examples of the usage of some of the stuff will be in a file, ced reu %.c. I use percent when I'm experimenting, or I have example, basically with debugging and experimenting with stuff, because when I'm done I might want to actually use just REU, so the percent just lets me know that that is something that I've been using to test the actual REU functions. So if I go ced reu %.c, there will be example usage for all of this stuff in here. And if we scroll down, see there's rdetect being used, checking for the return value, and there's rsize being used, and let's see, this will test the stash, fetch, and swap, and then it will proceed down here, and it will do some test screens, print up some test screens. I'll show you this program in just a second. And there's a stash, so it does a stash, it clears the screen, it does a fetch to make sure that it comes back on the screen. Then it also tests the swap feature and their swap function. And let's see, press return to test swap, and it comes down here into a for loop, creates a swap there, and here we go, and does a while loop, checking for the return key. As long as the return key is hit, the screen will keep swapping back and forth. So you can see, you can also look in REU %.c for some examples of this, of usage. Of course, all the programs in here, because of this video, will have some examples of usage, and I've included the REU header file here. Now let's go ahead and quit this, and let's go ahead and run REU% and watch it work. So this is a RAM expansion unit test, and I'm going to go ahead and press the key to start. REU detected, banks 8, 512K, and now I'm going to hit E to end, and when I do that, I've added this right here to test for the stash, fetch, and swap, and I'll go ahead and hit enter to continue. Oh, that's what I did wrong. I should have hit Y, but hold on, REU, percent, there we go, E to end, and I probably should have put a yes or no in here, but Y for yes, and then this will now test to see if we can stash data in the REU. Press return to begin. Press return to continue, so this is to be stashed. Press return to fetch. Pretty fast. And you'll notice the difference between when the screen is being printed versus when it's being transferred by the RAM expansion unit. It's a little bit of a noticeable difference there. You'll see the screen print, but when it does a swap between the RAM expansion unit and the screen, you just like it's page flipping, instantaneous. So here we go. Press return to swap. So you printed that. Now I hit return, swapping. Look how fast that is. Just instant. I can just fast. So then I just hit whatever other key. I get out of it. And that is that. This program I've also created a version that could be run from BASIC, and all the basic programs that can run, all the programs that can run from BASIC, they end with a .exe. So like DOS, and it's an executable file without requiring the PowerC shell. So I think that concludes our video. I appreciate you guys watching. I've got a new website up. You go to the website, you can download files, you can look at other stuff, and I'm still building the website, of course, but anyway, alright guys, I'll catch you in the next video. Bye.